So I said before that we're going to talk quite a lot about equilibrium, but what the heck does equilibrium even mean? Well, let's take it back to something we learned last semester. Last semester, we talked quite a bit about enthalpy. Enthalpy has a symbol of H. We drew enthalpy plots where reactants would be on one shelf and products would be on a different shelf, and the enthalpy change from reactants to products told us whether that reaction was endothermic or exothermic. Is this reaction endothermic or exothermic? When reactants are above products, delta H positive, negative? Delta H is negative, products are lower enthalpy than reactants. That's an exothermic reaction. Just a little recap. But what we didn't say then was that for reactants to be converted to products, there's really a barrier that has to be overcome. You have to go to some higher energy state in order to turn reactants into products. The truth is that happens whether it's an endothermic or exothermic reaction. So that plot on the right is exothermic. This little red plot I just drew is endothermic. Oh, it's hard to get those right sometimes. This one is endothermic, but there's still a hump. There's some sort of barrier preventing reactants from turning into products completely downhill slide. So this little plot we will talk quite a bit about this semester, but reactants are capable of going over that barrier, but additionally, products may overcome that barrier to convert back to reactants as well. We'll talk about that. Let's move along with what we're going to talk about specifically today. So we have seen that N2O4 can be converted into NO2 by this top reaction. One of these molecules decomposes into two of those molecules. What happened was, when you start a reaction, you have all reactants, all N2O4, but some of those molecules climb over that barrier to become into NO2. NO2. So not every single one races over that barrier all at once, but some of them climb over that barrier. As the reaction progresses, some more climb over that barrier, but once you get a little bit of NO2 accumulated, some of that NO2 can climb over the barrier backwards to become N2O4 again. This is a two-way street. Reactants can climb over to become products, and products can climb over to become reactants. We're going to talk at length in the future about the height of that hump and whether it's more likely to climb this way or that way, but maybe it's kind of intuitive. It's easier to climb a shorter hill than it is a taller hill, right? It's easier to climb an Appalachian mountain than a Rocky Mountain. Sure. So eventually you get this status where products are climbing backwards, reactants are climbing forwards, back and forth, but the rate at which the products are climbing backwards and the rate at which the reactants are climbing forward are equal. When the rate of the forward reaction is equal to the rate of the reverse reaction, that is the official definition of equilibrium. In the beginning, the rate was only reactant being converted to product. At this point, reactant is still being converted to products, some products being converted to reactant. But here, the rate at which reactant is converted to product and product is converted to reactant is equal. That's the definition of equilibrium. So, we saw a plot like this earlier. If we talk about the concentration of the reactant over time, it definitely decreases. The concentration of a product over time definitely increases. And as you may recall, we said, maybe it should be a little bit further to the right, we said the left area of that plot is called the kinetic region, and the right area of that plot is called the equilibrium region. That's because your slope is flat over here. There is no longer any changing slope in your graph. That's because the rate of the forward is equal to the rate of the reverse. There's no more net exchange of more reactants converted to products or more products converted to reactants. There's an equal exchange of both. But over here, we saw that the slope was not 0. The slope does exist. Those have different rates, and it's faster in the beginning than it is later. The rate stuff that we will talk about is called chemical kinetics. How fast does a reaction take place? It's all about reaction rates. I feel like I just gave you a very circular definition, but there it is. A reaction rate is officially defined as the change in the concentration of a reactant or a product over time. So we said molarity will be our favorite unit of concentration this semester. So molarity per second is our most favorite unit for rate because it's concentration over time. So if A is being converted to B, according to this little diagram thing down here, all the black dots are A and the red dots are B. And over time, A gets converted to B. And I should make you count these particles, and I was intending to make you count them. But if I counted, there are 40 black dots in the beginning and 0 red dots. And then there are 30 black dots and 10 red dots. Keep counting. 22, 18, 16, 24, 12, 18, 9, 31, 7, 33. Why did we do this whole counting exercise? Well, I want to point out that we lost 10, we lost 8, we lost math. 6, I think I did that math correct. We lost 4, we lost 3, we lost 2. Can you see that our number of particles that are changing are getting smaller? I hope so. But the number of tick marks on our little timer is the same every time. It's 2 little tick marks every time. So the exact same amount of time has passed every snapshot, every little picture, but we lost more molecules of black stuff in the beginning than we did toward the end. And eventually you would reach a steady state where you would have constant numbers of particles, but there would still be some being converted back and forth. What the heck? Hold on. Equilibrium does not mean that the reaction ceases to happen. I should say that again because you should write that down. Equilibrium does not mean that the reaction ceases to happen, but it means the rate at which the forward reaction is happening is equal to the rate at which the reverse reaction is happening. So we should maintain a steady state of something like this toward the end, but we still may be converting one reactant to product and one product to reactant, or 2 reactant to product for every 2 product that goes backwards. That's a real jumbled up way to say what I'm trying to say. The reaction continues to happen. It's just with equal rates backwards and forwards. Well, let me move along. I should probably even edit that out, but I ain't gonna. Okay. So if we're given this plot, we can talk about the rate in a couple of ways. We can talk about the rate of disappearance of a reactant. The rate of disappearance of a reactant would show up like this. Delta means change, so the change in concentration of A over the change in time. So this is any given time. Little t in chemistry means time, big T means temperature. So make sure that you use a little t when you're talking about time. So we put a negative out front because the reactant is always being consumed. This value here, that circled value, is always going to be a positive value. Rates themselves are positive values. So we stick a negative out front to indicate that it's disappearing at that speed. Delta A is changing concentration over delta T over time. If we're talking about the rate of appearance of a product, we don't put a negative out front because product is appearing at a positive rate value. So change in concentration over time for B, that's a product because it's increasing. A decreases, it's negative. B increases, it's positive. Okay, that was a simple example because everything was 1-to-1. What if everything is not 1-to-1? What if you have 2A reacting for every 1B? Reaction rates and stoichiometry, how does that work? The reactant that has a 2 in front of it disappears twice as fast as B appears. So that stoichiometric coefficient is important. For every 2 moles of A that disappear, a single mole of B is created. So the way we show that in a reaction rate expression is negative, because it's a reactant, 1/2, the reason it's 1/2 is it's 1 over the coefficient in front of A, delta T. B does not have a coefficient, so it looks exactly the same as it did before. What if you have many, many, many coefficients? Reactants are always negative because they are reactants, they are disappearing. The coefficient is 1 over the coefficient of whatever it is. So negative 1 over A, delta T, negative 1 over B, delta T, positive 1 over C, delta T, positive 1 over D, delta T. Yep. All of these are set as equal to each other, which is a pretty weird thing to do, admittedly. It's a weird thing to do. Why do we do that? Well, it's because the reaction rate, the rate of the reaction, could be described in various ways. The rate of the reaction could be described in terms of A, as in how fast is A disappearing. It could be described in terms of C, how fast is C appearing. So the reaction rate is dependent on what terms you're using to describe it. I would like to say a little bit more, but I think I can't say it in a non-confusing way, so I'm going to stop. One more little thing. Let's put some numbers in this instead of this 1 over A, 1 over B, 1 over C business. For the following reaction, at some instant in time, oxygen gas is disappearing at a rate of this. At the same instant, what's the rate of disappearance of NO2? Okay. I'm going to start by writing out that equivalence thing that was given on our last slide. The rate of the reaction could be described as 1 over 4, negative, 1 over 4, the rate of disappearance of NO2 over time. So 4 came to be a denominator, right? Or the rate of reaction could be described as negative 1 over 1, because there's no coefficient, delta O2 delta T. Or the rate of the reaction could be described as 1/2, positive 1/2 delta N2O5 delta T. So it could be described in any of those ways. What does that have to do with the question they're actually asking us? Well, if we look back at the question, at some instant in time, oxygen gas is disappearing at a rate of this. What they're telling us is this value. They're telling us that red circled value is 0.046 with a negative out front because my equation tells me so. At that same instant, what is the rate of disappearance of NO2? They're asking us disappearance of NO2. They're asking us to find this value. So right now, I don't care about the rate of the reaction. I don't care about the rate of appearance of product. I care about the green circled variable as it relates to the red circled variable. So I'm going to fill it in down below, even though I'm not answering the question that's actually written down below thus far. Negative 1/4 is equal to delta NO2 delta T. I'm just running out of space above. Negative 0.46 molarity per second. So hopefully you're not super rusty on math. Negative 1/4 means multiply this side by negative 4. So delta NO2, delta concentration NO2, change in concentration of NO2 is equal to 4 times that value. Let me get a calculator. Negative 0.184 molarity per second. So the rate of disappearance of NO2 at the same instant where oxygen gas is disappearing at 0.046, NO2 is disappearing at 0.184. Disappearing at negative is redundant. I'm going to try to color code and see if I can fit something else in here. At the same instant, what's the rate of this formation? That really means this orange thing that I've already X'd out in green. That orange thing is what I'm solving for this time. So I can choose to set O2 and N2O5 equal to each other using my given data up here. Or I can set NO2 and N2O5 equal to each other using my solved data down here. I'm fairly confident in my ability But sometimes I trust the numbers that are given to me more than I trust the numbers that I have found myself. So I'm going to set O2 and N2O5 equal to each other, and I'm going to unfortunately have to do that on the next slide. So I got negative delta O2 is equal to delta T. Sorry, over delta T is equal to negative 1, where'd it go? 1/2. Nope, positive 1/2 N2O5 delta T. So I know this is 0.046 molarity per second at the instant they're discussing. So that means delta N2O5 is 2 times that. Delta N2O5, yikes. Delta T is equal to, calculator, positive 0.92 molarity per second. Yep. This rate stuff that we have just discovered is called instantaneous rate. These rates are what are happening in the kinetic portion of the curve. This is not what's happening in the equilibrium portion of the curve. I feel like I should say that disclaimer. We got another round of equilibrium discussion coming up next as it relates to kinetics, but that's all for now.